Hi everybody and welcome to the second video of BIOB20. In this video we're going to see how to compute quantiles and how to plot histograms. In the second part of the video we will also see a new way to generate random numbers. We are going to work with a dummy example of the grades of an exam. In order to create a random sample that contains grades, we are going to start with set.seed1 to 3 so that we can all work with the same random example. Then we are going to create the sample with the function sample. Say we want to sample grades from 1 to 101, so we say x equals 101. It is possible to sample the same grade multiple times, so we say replace equals true. The reason for sampling from 1 to 101 is technical, and it will be apparent in a minute. Finally, we assign the result to the variable x. When we press enter, nothing happens on screen. If we want to see the sample, we have to type x and press enter. This displays a vector of 101 values. For long vectors like this one, we can see how useful these indexes on the left are. The first value is 31, the 31st value is 76, the 61st value is 79, and the 91st value is 12. The last value is 23 at position 101. We know it is position 101 because we have asked for a sample of size 101. At that point, one question we can ask is what grade does it take to be in the top 10%? The first thing we need to do is sort the grades from lowest to highest. This is exactly what the function sort will do. You can see that the lowest grade is 4, and the highest grade is a lucky student who got 1 bonus point above 100. The grade that makes the cutoff for being in the top 10% is such that 10% of the grades are higher and 90% of the grades are lower. This is the grade at position 91 and that grade is 93. There are 10 grades that are equal to or above 93 and 90 grades that are equal to or below 93. The reason we chose a sample of size 101 is to make these calculations easier. This strategy shows how to use the function sort to find the grade that makes the cutoff for being in the top 10%. But there is a more direct way to do it, which is to use the function quantile. The command quantile x, 0.9 requests the quantile of the sample at position 0.9. As you can see, the output is expressed as a percentage, 90%, and the value is of course the same as before, 93. By definition, the quantile at position 0.9 is the cutoff such that 10% of the values are higher and 90% of the values are lower. This is exactly the same definition as the one that we have implemented manually with the function sort. To give another example, we can see that the quantile at position 0.3 is 31. We can also see this in the sorted vector by the fact that the value at position 31 is 31. 30 values are lower than 31 and 70 values are higher than 31. This is what makes 31 the quantile at 0.3. Another thing that we can ask is to have a complete representation of the sample. We can do this by plotting the histogram, which we do by typing hist_x. When you press enter, R will draw the histogram of the distribution. You can resize the window a little bit so that it fits on your screen, and you can move it to the right so that you have space to see what you're typing next to the plot. On the y-axis of the histogram you can see the frequency, which is in reality the total number. That is to say the number of elements in the sample that are within the buckets indicated on the x-axis. For instance, between 0 and 10 we can see that there are 8 students. Between 10 and 20 there are also 8 students. The histogram of x represents the global distribution of grades in the class. We can ask once more what is the cutoff to make it to the top 10%. We can do this with the function abline. It adds a straight line to an existing graph. Here we want a vertical line, so we say v equals 93. This is the position where we want the vertical line to appear. 93 is the value that we have previously computed to make it to the top 10%. To make it a little bit more visible, we say col equals red between quotes. This indicates that the color of the line should be red. As you can see, this adds a line at position 93 on the graph. Having a grade that is right of this line makes you part of the top 10%. Another way of saying this is that 10% of the surface of the histogram is on the right of this line, and 90% of the surface of the histogram is on the left. This is another way of thinking what it means to be in the top 10%. This is also another way of thinking of the output of the command quantile x, 0.9. Now let's go back to an example that we have seen in the first tutorial. We were drawing patients who have either received the placebo or the vaccine. We were doing this by using the function sample with x equals c0, 1, where 0 stood for placebo and 1 for vaccine. We were also using size equals 196 because there were 196 people who had symptomatic COVID-19. And we have to say replace equals true, otherwise the call fails. This is a way to produce samples of 196 patients, where 0 stands for placebo and 1 for vaccine. We were interested in the total number of people who received the vaccine, which in this case we can do with the function sum. This adds the numbers in the vector, and because here we have only ones and zeros, the sum of ones is the number of people who received the vaccine. What is interesting here is that we have created a process that creates a random variable of size 1. We go from a size of 196 to just one number, the number of people who got the vaccine. In that sense, we have created a random variable that goes from 0 to 196. The R programming language has a function to do this more efficiently. This function is called OR_binom for resample from the binomial distribution. This works by first specifying a size which is the highest possible number we can get, so here 196. Then we specify the probability for the appearance of the number 1, so here 1/2. The last parameter we need to specify is how many samples we want, and here we want just one, so we're going to say n equals 1. When we do this, we get numbers that are very similar to the previous method because these two methods are equivalent. This is a shorter and more efficient way than the commands that we had before. One important advantage of this method is that we can increase the value of n to create in one go multiple samples that come from this complex distribution. For example, we can set n equals 100. This is a much more compact and efficient way of approaching this type of problems. In the tutorial, we also changed the probabilities of zeros and ones. For instance, we were considering the cases when there are more zeros than ones. One way to do this is to go back to the sample function and use the prob parameter. Using this parameter, we could say that the probability of observing a 1 is only 1/5 of the probability of observing a 0. With this sampling method, the numbers were smaller than before because, of course, there are much fewer ones than before. Internally, OR rescales the prob parameter so that the probabilities sum out to 1. This comes out to computing 0.2 divided by 1 plus 0.2. So the probability of 1 is 0.16666. Going back to our binom, we can obtain the same effect by changing prob to 0.16666. Once again, the processes are equivalent, so we get similar values. Again, the main advantage of using OR_binom is that we can use a much higher value of n, like 100 for instance. We then obtain larger samples with a distribution of interest. With this method, we can sample distributions coming from different null hypotheses. This is what I wanted to share with you. Good luck with the quiz and see you in class.